All right, are there any questions? Any other questions? The stack is still created. All right, so let's drop back for chapter 33, and hopefully something somewhat coherent.
Are we gonna pick up on 33 where we left off, or are we gonna just start over again?
How much of 33 did I actually do? I think
I thought you done chapter 34.
we did mostly what we did yesterday was 34, but
Yeah. The law of magnetism or magnetic or something like that.
oh, the whole how do electromagnetic waves get created?
Something like that. Faraday-Lenz's law, that's like that.
Yeah, that actually that shows up. Oh, there's my marker. This is the AC circuit stuff. That's not there. Yeah, I guess it's sort of picking up there. Okay. So that stuff was section 33.1 and 2, or I guess 33.2. If I can separate pages. That's when it gets into the propagation of light. All right. Sort of flash back just a little bit. When we were talking about wave production, we still have the equation that V is equal to the frequency times the wavelength. And that holds just as well for light as it does with mechanical waves. The difference is that instead of V, typically for the speed of light, we use the letter C. And then the others stay the same. So there's a whole lot of electromagnetic radiation of just different frequencies, some of which we can see, some of which we cannot see, some of which we feel, some of which cooks our food. So the wavelength for, say, a microwave, for example, is, on the order of somewhere in that range right there. Yeah. Still planning to do the Hershey Bar experiment. I don't know if any of you have done that. Get Hershey Bar into the microwave.
Oh, yes, I have.
You have?
I have, well, not that, but the ink that is in erasable pens.
Right?
Erases through heat. So if you put it in a microwave, you can see the wavelength if you just scribble on a piece of paper.
Ah, I like that.
You can see where the waves hit the paper.
I assume you keep the paper still?
Mhm.
Okay.
Yeah, you just, the one where the paper is still,
How long do you cook it?
I don't know, like a minute.
Okay. All right, so basically what's happening, the chocolate bar thing is you put the chocolate bar into the microwave and you basically turn the turntable over so that it's not turning. And if you do it too long, you just have a melted mess. So you need to do it just the right amount, which is anywhere from 20 seconds to 3 minutes, depending upon which source you look at. And there should be some melted marks in the chocolate, which corresponds to, I believe it's half the wave, that's half the wavelength. Because if you think about a wave, and the chocolate bar sitting right there, it's getting hit. Ish. And I guess the invisible or the erasable ink works similar method. So visible light, you can either express it in terms of frequency or wavelength. Traditionally, wavelength, and so visible light is somewhere around, well, depends on the source again.
400 nanometers to 700 nanometers?
I got 380 nanometers in one source and 400 in another source. And the biggest I got, I saw 740, 750, and 760. So somewhere in that, basically visible light. Now, within this, you get the colors, And so red is over here and violet is over here. Now, what are the exact bands for the colors really depends on the source you're looking at also. Because if you ever looked at the spectrum, look close enough, you know, at what point does it change from, say, orange to red? Well, you know, there's that I'll say gray area, not a figurative gray area, or it's really not quite sure which color it is.
Discrepancy.
See?
Discrepancy between them.
Yeah, there's definitely a discrepancy there. And so the textbook seems to be going by, in essence, I looked at 3 different sources to try to figure out what was considered to be red, and none of them agreed, but most of all, they all did agree that what the book wrote was wrong. So. So, I'll talk about, there's one particular example problem where the book is actually makes 2 or 3 different things that would be considered mistakes by some other people. All right, so within this, you got the different spectrums, and part of this is based upon the visible. It's basically the way we've evolved, and we've got fluids inside our eye which absorb the radiation of different types, and so this is the stuff that gets through. So in terms of energy, and this is sort of a leap ahead, the book does it too, is that when you're talking about the energy of light is equal to h times the frequency. So if I take a piece of red light, let's take at the lower end of the spectrum here, we'll just take 760 nanometers. And I want to figure out how much energy is in a beam of red light at that frequency. Well, first off, what is nano?
Billion to
Okay. So 760 times 10 to the negative 9 meters. So that's my wavelength. Speed of light is
299,792,458 and back.
I was going to round it off, but you said it with such confidence, I'll assume that's right.
Yeah, that's right.
Okay. And then we just plug into the formula there. I know that the frequency is equal to the speed divided by the wavelength. So we got that 299,792,458 meters per second divided by 760 times 10 to the negative 9th meters. 760. And if someone would be kind enough.
And that's the speed of light right there?
That's the speed of light right there.
Okay.
Is 3.944 times 10 to the 14.
Units?
No, hertz.
Hertz. So you could express this same bit of light in terms of its frequency, but typically not. However, we do need to know the frequency in order to figure out the energy of it. Now we have this h right here, which is known as Planck's constant. And Planck's constant deals with trying to resolve what's known as black body radiation, that if you have something that will absorb. So the best that we can do is to paint it black so it absorbs as much energy as possible. Put a little hole in it so that only certain radiation will escape. What we were seeing of the radiation that was coming out did not match our theory. Matter of fact, it didn't even go, well, it matched it for a tiny little segment, but for the most part, it did not match at all. And the prediction, which they knew was wrong, was that ultimately the entire universe would be destroyed based upon what the prediction was. Until Planck came along and resolved it, but in order to resolve it, it required creating this number right here, which turned out to be incredibly important. So the energy of light is this number, which is 6.626 times 10 to the negative 34 joule seconds, times our frequency of 3.944, times 10 to the 17th hertz. Again, so it would be kind enough.
Uh, 2.6137 times 10 to the negative 19.
Units?
That's joules.
Yep, that's joules. So that's the amount of energy that would be in a photon of red light at that frequency, or that wavelength. Now going to the other end of the spectrum, I want to just go through the same exercise except at the other end at 380 nanometers. And so, first find the frequency. So, which is the 299792458 over 380 times 10 to the negative 9.
.889
7.889.
times 10 to the 14.
And now we plug it into our energy equation, so we just multiply that times 6.626 times 10 to the negative 34 joule seconds. Somewhere around 6 times 10 to the negative 19.
5.2274 times 10 to the negative 19.
So the violet light has higher energy than the red light. But red light has a bigger wavelength. There was a kid's toy by Play School, they had a little rocker here, and they had that tower in the middle, and then you had the different rings that went around it. And if you have this,
Yeah,
kid?
I know what you're talking about.
Simon's, right? Is it
Yeah, I know.
Simon?
I don't remember what it was called.
No, it's not, it wasn't Simon Says. It's, I know what you're talking about.
It's all plastic, no batteries, if that's what you were thinking. So they used to have it so that red was at the bottom, red was the biggest one,
Oh, I know what you're talking about.
and it was the farthest down, which was great from a visual of red was the lowest energy, so farther down, and it was also the biggest wavelength. And then at some point they decided, well, we put red on top. Completely ruined it for physics purposes.
The 5.2274 times, what's the 10 raised to?
The negative 19.
Okay.
And that's a J at the end.
Yeah. I was thinking it said 101, I was like, that's a little high.
Yeah,
A little low.
that was a little high. Same exponent as the other one.
Oh, okay.
All right, so microwaves have an even longer wavelength. They have a lower energy, and ultraviolet, shorter wavelength, higher energy. And go from there. All right. So let's take a look at some of the vocabulary, because as light is projected outwards, too many cross-purpose notes here. There are various ways that we can sort of quantify what's happening. So as light is produced, so I take a light bulb, just as an example here. It's a light bulb with light coming off of it. There's something known as the radiant flux, or radiant power. Different sources call it one, different other sources call it the other, which is a measure of how much energy is being used per second in order to produce this. In other words, what's coming off of this light, probably better wording, it's the energy that is coming off of the light in whatever form. Now, in the case of incandescent light bulbs, a large portion of that is heat, not actually usable in terms of actually, man, having trouble transitioning.
In terms of actually producing light.
Yeah, for visual things. I'm just full of the good words today. All right. We'll muddle through it. So the units are the units of power, which is watts. However, typically with a light bulb, you want like it to produce light. And so another measure of this actually is the luminous flux. Luminous flux. Which is a measure of the radiant power that is actually visible.
You go on Lowe's, they put it at Luminous.
Say it again?
Like if you go buy these new light, fixtures, and they ask you how many luminous power that's gonna be at a certain amount of hours that you have for that. So you might have to buy another one.
Yeah, there is a switch now, instead of telling you the watts, in other words, how much energy it's gonna use, it gives you in terms of brightness.
Yeah.
What they're trying to do is shift people away from, I need a 100-watt bulb, to, I need a 1600 lumen bulb, so that you can buy something that uses less power, if all you care about is how much brightness there's gonna be. The symbol that the book uses for luminous flux is F.
Got a lot of F's.
Pardon?
So you got a lot of F and symbols.
And it is the measure of brightness. Brightness in quotation marks. Now, the reason why I have put brightness in quotation marks is that not all colors are seen equally as bright. And so it is really a measure of brightness, and on the package it says brightness and the number of lumens it is. But it's not necessarily a measure of the amount of power that is in each color, but there's a certain proportion for each color. And what has been found is that for the average human eye, not necessarily yours, but for the average human eye, the color that we see the brightest is 550 nanometers. That's the one that seems to excite the back of our eye the most.
Feel like
Yeah, I think it is
Little above green.
let's see, 555 is in the green, closer to the yellow side.
Yeah. Green, yellow.
Is that Kelly green?
There's a tool that you can use to measure how much red, blue, yellow, green, whatever light is in a particular light bulb with a certain camera.
Oh,
I don't know what the tool is
okay.
or how much it costs, but it's pretty cool. And you
Yeah.
can see, because in certain light bulbs, like fluorescent light bulbs, there are spikes of light in the ultraviolet range, which is not good. And I think LED and the incandescent bulbs are the best. That doesn't have these spikes. They're just,
Oh, okay.
yeah,
So incandescent and LED, you said?
yeah. But, I mean, don't usually get us.
If you find the name of that, just send me an email.
Yeah,
Thanks.
I'll see, there's a video, a YouTuber makes a video on it, and he explains it pretty well. I don't know what it's called though.
Alright. So if we are looking at the radiant power of this particular wavelength, if that's what it, you know what, I think an example probably is gonna work the best here. So if I have I'm just gonna use the example from the textbook. This is example 33.3, and just note there will be some differences between what I say and what the book has. So it is 600 nanometer wavelength of light. This is what they are talking about, and they mentioned that it is red, and I will say that the three sources that I looked at all put that in the orange range. None of them put it in red. So, orange. Orange yellow, it's in that, on that borderline right there. 4-watt bulb. So if it were, if it were 555 nanometers, if that was all the wavelength that's coming out, then we can find the luminous flux easily enough by just multiplying them, or sorry, multiplying times the conversion factor here. So it's 683 lumens per watt times 4 watts. And this is another place where the textbook disagrees. The textbook has 680, they seem to have rounded off, but I saw several different sources which all said 683, so I'm going with 683. And if you multiply that out, 2,732 lumens. And by the way, somebody mentioned it before, I believe, or it has come up in conversation. The units, the SI unit for luminous flux is the lumen. So 600, so we'd have this number of lumens of brightness if it were 555 nanometer wavelength, but we're at 600 nanometer wavelength, and so we're gonna be some fraction of this. We're not at that max